Hey there. Doing this in the morning. Hope to get it posted before you all are up. Going through 25 and 26. I probably will get through chapter 21 this afternoon. 25, we talked about it at the very beginning of this chapter, probably section 20.2. If I've got current going through a conductor, we've got magnetic field created around that. Now, that is, apparently green is not what I want to use. And these loops are kind of hard to see as far as which way is in front, which way is in back. So we use that right-hand rule with conventional current. And we use X's and we use dots. So remember those X's and dots because those will help in 21. If I put my thumb in the direction of the current, the field is coming out. I hope this comes through. And we use dots. AP will do circles around it. I'm just lazy. Because that's how I am. And so we can show our field coming out of the page on this side and going into the page on the other side. Now, we know it creates a magnetic field, but the chapter jumped right into force. It's probably because we could see it, and that's kind of cool. But if I've got a current going through a magnetic field, we experience this force of either oppositional or attractive magnetism, right? As far as magnetic forces. That means this is creating a magnetic field. So 25 really that's my lamp, that's my screen, really just gives us an equation that ties in field strength, right, with a current carrying conductor. So B is our field strength, or our magnetic field. In what unit? Yeah, I heard that. Tesla, right? We had it related to, if I increase the current, clearly that's going to make a difference. And then my distance away, right, this radius should make a difference also as far as field strength, because way over here is going to be a lot less than really right close to the current carrying conductor. And so reduce the radius, increase the field. That is an inverse relationship. Now that's proportionality statement. I mean, I should have a little proportionality, but they've got some constants that go through it. And that was mu naught over 2 pi, okay? So, and naught doesn't really show up. So that mu naught, what was that? Can I get that in the screen a little bit? I think it was 4 pi times 10 to the negative 7. And of course I should have units to it, but I don't right now. Maybe that's your job, right? But I'm definitely going to have Teslas, right? I'm going to have current, and I'm going to have meters, and that probably works it out. So mu naught. Okay, so that is 25, and I'm going to just pause. Boom, I've changed it to 20.6. Sorry, I was pausing and erasing my board and getting it set up for 26. So if a current carrying conductor carries a field with this relationship, right? That means, and they also experience a force inside a magnetic field, then we should be able to get the force if I've got two current carrying conductors side by side. And we know there's a relationship on the direction of the force. So why don't I just, expand that. That was interesting. I was like, why is this so small? There's a relationship. If this is producing a field, this doesn't know it's a current carrying conductor experiencing a field. It just knows it's got a magnetic field there. So we kind of have to put ourselves in that spot. And this one right here, current 1, is experiencing a magnetic field but doesn't know what front. It could be a magnet or it could be a current carrying conductor. So we're going to say right now, if I'm going to produce a field, it's either going to be out of the page or in the page. And so the current carrying conductor is perpendicular to the field, so I'm going to just get rid of that. Okay. So we're going to go through it. I'm going to say, well, what is, right, the force on current carrying conductor number 1, right? So, well, let's see. The force on it definitely depends on current 1. and the length of it. Now we're going to assume the length is equivalent. But the field, what is that field? Well, it is this field, okay? So this field is produced by I2. Now what is I2? That is mu naught, just a constant, 2 pi, just a constant. Now this field is related to the strength of I2, and instead of R for this equation, the AP equation sheet puts this as D, which, I mean, let's be honest, it's about the same thing. This is a certain distance away. So they'll use D right there, okay? So I could rearrange all this, but I'm going to look at force on 2, right? Now that would be dependent on how much current I have in 2 and its length, and the field would be produced by conductor 1, so that's mu naught. That's an awesome mu naught. Pi, sorry. Mu naught. What is that symbol, Ms. Falkenberg? Oh, glad you asked. That's a mu naught. And then the field that it's experiencing is from I1, so that's I1 over D, right? And if you look at these two equations, you'll see that everything is the same. So what they're getting is equal forces in magnitude. So now let's talk about direction. I'm going to use some red pen, see if that shows up a little bit better. Let's talk about red is the field produced by, I guess, current carrying conductor number 2, right? So if I go down, right, and I use my right hand rule, it's going into the page on this side, and it's out of the page on this one. So I'm going to do into the page and extend it into the page, okay? And then we modify our right-hand rule because that was just finding around a current carrying conductor, wrapping around it. But now I want to know where the force is. My force is my thumb, my field is my palm, fingers is the direction of the current in the wire. So I've got, let's do this. I got my current up, but my field is in to the page. So my force, right, that they'll experience, right, this is force on current carrying conductor 1 by 2, right? Now, you should remember that these are equal in magnitude, and then the concepts from Physics 1 is opposite in direction. But we'll do the same thing for current carrying conductor number 2. So I'll go over here. This is hard for me. I'll wrap around I1. What's happening on that side? It's coming out of the page. And this side, it's going into the page. So also into the page. Okay. So here I go. Field, into the page, current down, force, right? This is force on 2 by field 1. Okay? Now what I didn't mention when we talked about 25 is the fact that these strengths, these field strengths, have the magnitude and a direction. Okay? That means you can use the principle of superposition. So the field in between here, right? This is a totally different subject. But if I were trying to find the field inside these, it would be basically double the field strength in between here because they're both going in and they're adding up. So if I did that here, but I looked at it, do I have room here? This is these are conductors. I1 and I2, right? And they're going into the page, and that means their field lines, right, into the page are going this way, and field lines, right, let's see, that way, and this one, oh, maybe I did that wrong. Oh, I forgot I2 is coming out of the page. There we go. So I1, I2, it's coming out of the page, so that field is going down also. if I were to evaluate the field at this point, I'd have B1 and I'd have B2. So again, these are vector quantities. They have a magnitude and direction, so they will add up. B1 goes down, B2 goes down, so by virtue, they just add up to each other. If they were in the same direction, they'd cancel out, so the field would be less between those. Okay? I've gone over my time. I hope this works, and I hope it's helpful.